Next few weeks, because now we are gradually moving to gradually we are going to be moving to deep learning based vision. Okay. And because in the deep learning class I'm already covering some of these aspects. So next, maybe 3 lectures. For Monday, what I'd like you to do is, if you guys are able to come to the deep learning class, which is today, meaning Monday, what is it, 1:30 to 4? Okay, if you're unable to come to the lecture, then of course it will be recorded. Contact me and I'll give you the recording of it. So rather than me repeating the same thing there, repeating the same thing over here. So next 3 lectures. On Mondays, we won't have a class for today. I'll give you some background, but from next Monday, you guys will come to this class if you can make it. If you have a conflict, contact me for the location of the lecture, video recording of the lecture, right? So, however, on Wednesdays, we'll continue with the material that we need, which is different from deep learning, so that you guys keep learning all the necessary mathematical, vision-based background that's needed, right? Okay, so today, because I'll be covering what are called deep convolutional neural networks in the deep learning class, for the benefit of those of you who don't have the deep learning background, I'll just give a quick, maybe 45-minute review of the neural networks, so that once you come to the lecture, you're able to follow. Okay, so once again, no class on Monday for computer vision, but you guys will come to the deep learning class next Monday. Wednesday, we will have a class. Okay. Yep. Okay, so see with computer vision. Okay, remember our overall goal is to be able to detect objects and recognize objects. Before we do anything more advanced, such as a self-driving car or a sequence of activities based on what we have perceived through vision, right? There are, of course, classical techniques for both of these, which we are trying to learn as part of the theory of this course. And then the most modern is the deep learning techniques. Okay, so for example, let's take a look at object detection. A classical technique that we will cover the theory on one of the Wednesday lectures will be based on Haar transform. Okay, in the algorithm, which is very famous, this is called Viola-Jones algorithm. Okay, and the fundamental idea in this algorithm, and we'll go into the detail of this later on, but just to give you an idea, is what we create what are called Haar features. Okay, so for example, let's say here's a face. Okay, so in the Viola-Jones algorithm, what we do is we create, and you guys have seen a little bit of these Haar features when we were discussing SIFT and SURF as an example, right? So for example, we create a rectangular area, okay, where we will take the sum of pixels in this area, subtract it from the sum of pixels in this area, and that will give us some value, right? So sum in this area minus sum of pixels in this area. So that value is called the Haar feature as an example. So same way, we have windows like this of different sizes. We have windows like this, windows like this. So basically, we create many, many different size windows on a given image and compute what are called Haar features. Then based on these features, then we create a classifier so that it can give us a decision whether this is a face or not. And it works in real time, does a very good job. So anyway, like I said, we'll go into the theory of it, detail of it later on. So that's one of the classical techniques, right? So now, using deep learning technique, what we can also do is we can feed in an image. So here's some image, right? And to a neural network. And the neural network can decide if it is a face or not. Okay, so hopefully towards the end of the course, once you have learned this, and I'll show you the code for this, then you will create your own network to be able to detect the face. Then you guys will compare yourself, which one is better, which one does a better detection, which one doesn't, right? Okay, so that's an example of object detection. Okay, same way we can have a car detection, tree detection, soccer ball detection. So it doesn't have to be face, it could be any type of detection, right? Okay, then comes the recognition part. Okay, as far as the classical techniques go for recognition, okay, for recognition, for example, you guys are working on the current technique, the PCA, Principal Component Analysis. Okay, so let me briefly review this. How does this work? Okay, so if you recall in the PCA, what we do is first we create the basis vectors. Okay, so for example, let's say you are given faces of, let's say, 200 people. And let's say each one is 100 by 100, right? So if you recall, what we did is we created first some kind of a matrix where, suppose this is I0, this is I199. So we did I0 minus I bar. So this is the average image, right? And then we did I0 minus I bar, then I0 minus, sorry, I0, okay, I1 minus, sorry, it should be 0, 1, yeah, I0 minus I bar, I0, I1 minus I1 bar. So if I1 tilde is the average image, right? So basically, if you recall, we create a covariance matrix. Okay, so this is our covariance matrix. Okay, so if every image is, let's say 100 by 100, right? And if we convert it to a vector, you can see it will be a 10,000 by 1 vector. Okay, so if we did the inner product, so meaning I should do a transpose over here, transpose over here. So 1 times 1,000 times 1,000 by 1, you'll see will give us just a single number, right? Okay, So if we had 200 images, this size will come out to be 200 by 200. And as you can see, what it's doing is, it is giving us the relationship between one image to the other image. And then we compute basically the eigenvalues. So in this case, there will be 200 of these. We sort by magnitude. Okay, and let's say keep top 50 as an example, or top 30, whatever, right? We create eigenvectors corresponding to the top 50 as an example, right? Okay, so then after that, we can create the basis vectors. So if our I matrix was basically an assembly of 10,000 by 200 of these, each row is basically the mean adjusted image. Okay, so then our eigenvectors over here, our EV matrix over here, if you take a look over here, will be basically, if we were just keeping 50 of those, so that will be 50 times 200. Because each eigenvector on a 200 by 200 matrix will be 200 by 1. And since we're only keeping 50 of those, so 200 by 50. Okay, so anyway, so then once we multiply now the I times EV, and if this is 10,000 by 200, and if this is 200 by 50. Okay, so you can see this is what we call the eigenfaces. Okay, so our EF matrix will be basically 10,000 by 50. So essentially, so this is our EF matrix, 10,000 by 50. And if we looked at each one of these, you will see it will be like a ghost-like face. Second one, ghost-like face. Okay. So now if we take any unknown image, right, which is basically 10,000 by 1, and subtract the mean from here, and we try to project it onto our reduced bases, which are only 50 dimensions over here. So basically, as you guys saw, if we did the we wanted 1 by 50, right? So if we did a transpose times EF, so this will become minus I bar, okay, times EF, so EF, so this will be 1 by 10,000. This is 10,000 by 50. So this will be basically projection of incoming image or the unknown image onto the 50 faces. Okay, so this will give us basically I projected, which will be 1 by 50. So as you can see, what we have done essentially is we have reduced 10,000 by 1 image to simply 50 numbers through the PCA, right? So now if we take a look at all of our 200 faces in our data set, and then saw which one of these correlates to or has the least Euclidean distance with the projection of each one of those 200, then we can say, oh, this incoming input matches, for example, image number 57, right? Okay, so anyway, this is a classical technique. So keep in mind as we go along, especially as we take a look at the deep learning techniques, one thing you will see is there's always a very close relationship when we develop the deep learning to a classical technique. So it's important for you to understand this way. Actually, you can make it even better with that background, right? So how can PCA be accomplished through deep learning? Okay. At first, you might say, oh, there's so many complicated steps over here. There's calculation of the covariance matrix, calculation of the eigenvalues, eigenvectors. Then there's the creation of the basis space over here with 50 of those basis vectors over here. Then projection of an incoming image onto these 50 dimensions, right? So it seems like this is way too complicated to be able to be solved by a neural network. Okay, so now let me give you a tiny bit idea of neural networks. Then I will answer how this PCA can actually be accomplished. Okay, so okay, so now let's take a look at a neural network. Okay, neural network is actually, as most of you have already seen, is a very simple computational architecture, right? It basically has a summation unit. It receives inputs like x0, x1, xn. These are the inputs. It multiplies them by some weights. Okay, then it adds them up. Okay, there's always an input with the value of 1. Then it multiplies it with a value which we call the bias, right? Then it passes it through an activation function. And so this is how a single neuron looks like. And then produces some output. So let's call this, because this is the output of the sum unit, if we call it S, this is what we call the activation function. Okay, so let me call this output A for activation or A for actual, whatever you want to think of it, right? So for the benefit of those of you who are new to this, let's pick a very simple example. Let's pick where our input is, let's say, 0.5. This is, let's say, 0.8. Okay, and let me just put 2 inputs for right now. So pretend just 2 inputs. And let's say bias right now is 0.1. Okay, so what will be the value of the sum? Sum, as you can see, will be 0.5. Weights in the beginning are initialized randomly. So let me pretend this is 0.2, this is 0.3 in the beginning. If that was the case, then what will be the sum? Very easy, 0.5 times 0.2 plus 0.8 times 0.3, right? This time this plus 1 times 0.1. So whatever that number is, so obviously this will be 0.1, this will be 0.24 plus 0.1, so this will be 0.44, as you can see, right? So after the neuron adds all the inputs by multiplying them with certain weights, then it passes them through an activation function. Okay, one of the popular activation functions is called the sigmoid. Okay, sigmoid looks like this, fx equal to 1 plus e to the minus x. So for example, x is the input, f of x is the output. Okay, so for example, suppose x is 0. So if x is 0, then what will be f of x?
0.1.
E to the 0 is 1, so 1 plus 1, 2, 0.5, right? If x is very large, like 100,000 or something, then you can see this will become, because of 1 over e to the x, so this will become almost 0. So if x is large, f of x will be close to 1, right? If x is negative and large,
Close to 0.
so then this will become positive, it will become a huge number, then f of x will become close to 0, right? Okay, another thing to remember is if we take the derivative of f of x, okay, and you can do like a u over v type of formula either way. If you took the derivative of it and if you try to simplify it, what you will notice is this will come out to be f of x times 1 minus f of x. Okay, so once again f of x is the output, x is the input. Okay, so let's pick this example. If s is 0.44, we pass it through a neuron, then how is a related to s if this is a sigmoid function? So you can see this will be a equal to 1 over 1 plus e to the minus s, right? Because s is same as the x, that's the input. So this will be 1 over 1 plus e to the minus 0.44. Okay. If we try to plot this, you'll see the sigmoid looks like this. Okay, so right at 0.5 it passes. Okay, so this is x, f of x. So if x is 0, the output is 0.5. Okay, so in our case, what was the input over here? 0.44. So can you guys guess what will be? So let's pretend over here is 0.44. So I don't know, maybe it will come out to be 0.6 or 0.7. So that's how we can compute the output, right? Okay, so this is how we create a single neuron. And the purpose of the sigmoid, as you can see, is to make sure the output stays between 0 and 1 range. Because if it's a negative large number, output will be 0. If it is positive large, output will be 1. So activation function basically forces the output, if it is sigmoid, between 1 and negative 1. Between 0 and 1, right? Okay. Now, the purpose of a neuron is basically, as you can see, let's pretend this is not there. If this is not there, then if this was not there, right, then what will be the output? Output will be
Sum.
A equal to W0 X0 plus W1 X1 plus 1 times B, right? Okay, so these are just numbers, right? Okay, given to us. Okay, sorry, that's the input. Weights are after we have trained our fix. So this is 0.2 in our example, 0. If we try to draw this out, right? So basically this will be like some kind of a surface over here, like a straight type of surface in 3 dimensions. So x0, x1, and then A is our 3rd dimension, which is the output over here. Okay. So essentially a single neuron is like a separator. If we had a lot of data, some X's, some O's over here, so it will tell us how is the decision boundary which separates the 2 data. Okay. But a single neuron will always be like it will create like a straight line or a plane in higher dimensions to separate the data. Okay. Sometimes our data could be separated like this. Okay. So if we wanted a classifier, so that if it is above this curve, it should be treated as an O. If it is below this, it should be treated as an X. Then typically what we do is we put multiple neurons in multiple layers. So a general neural network looks like this. Okay. Okay. And we have some inputs X. Okay. Suppose we had, let's say, 3 inputs. X0, X1, X2. Okay, so what we do is all inputs go to every neuron. Okay, so for example, there could be W0, W1, W2, right? The same 3 inputs will also go to the second neuron. So we'll also go. Okay, and suppose this is W4, W5, W6 as an example, right? And so on. So for each and every neuron, all inputs are fed. Okay, this could be W87, W88, W89. Okay, so for example, let's say I have 100 neurons over here. Okay, I have 3 inputs over here. Each one has its own set of weights as it goes to that neuron. So how many total weights will there be?
100 total.
So total number of weights. Will be 3 times 100, right? 300. And each one of them has one extra input called the bias. This could be B1, B2, let's say B100. Okay, so there will be 100 bias inputs, 300 weights, deciding how this should be summed, then further passed through the activation unit, right? Very similarly in the last layer also. Now we have 100 lines going over here. All 100 of them will go over here. All 100 of them will go to the second and the last neuron. And then we produce some outputs over here. Okay, so the fundamental problem in neural networks is, so let's pretend we had 10 neurons over here. 3 inputs, 100 neurons over here. So in the beginning, weights and biases are initialized randomly. Then through training data, we learn these values. meaning values of weights and biases, right? Okay, so these essentially weights and biases. So let's pick our example. Can you tell me how many parameters do we have to learn? Okay, how many weights were involved over here? 300. How many weights will be involved over here? If there were 10 neurons here,
10 cross 100.
100 times 10,
neurons times.
right? 1,000 over here,
Yeah.
plus 10 biases. Each neuron has its own bias. Here we had 300 plus 100 biases.
Yeah.
So the total number of parameters that through training we need to figure out what should be the optimum value of those, as you can see, is
300 plus 100.
300 plus 100, 400, plus 1,010,
1000 plus 10.
so 1,410. Correct? Okay. The general terminology for these weights and biases is theta. So theta is what we call the model parameters. So as we go through more advanced research papers, often you'll see they'll be indicating, the whole model. They'll be writing as a Greek letter theta. Once again, what does theta mean in this case? Each one of those weights and each one of those biases. Okay, so the question is, let's say we were doing digit recognition, right? In a digit recognition, our input will be something like this, 0, 2, right? Okay, let's pick an easy case. Suppose this is, or let me pick, because you'll be playing with it soon. So let me pick, there's a data set called MNIST. Those of you in the deep learning are very familiar with it, but it is a 28 by 28 grayscale image. Some of them have 0 digits, 2 digits, 7, 8, 9. So there are 10 types of digits over here, right? So if we wanted to design a recognition neural network such that if we feed in a 2, it tells it recognizes it as a 2. So in that case, what we'll do is, first, very similar to the PCA, we will linearize all the pixel values. Okay, so if I put 28 values over here in the first row, then the next 28, and so on. So if I assemble all the rows in a vector, you will see this will come out to be 28 times 28, which is 784 times 1. So each one of these digits will be fed to our neural network as 784 inputs. Okay, so these 784 inputs now will go into some weights, then into 100 neurons as an example, because output has to be one of the 10 digits, since we know that in advance. In the second layer of neural network, we'll only put 10 neurons. Okay, so now let's pretend the network is trained properly. Okay, somehow we trained it. How do we train it? I'll talk about it in a few minutes. We feed in, let's say, a 2.